Greetings, this is week 6 of our course and we are heading to the end of our course already. In this week, I'll deal with the structural considerations and application for 3D concrete printing. You'll hear the different types of current reinforcement techniques for 3D concrete printing, structure analysis and design considerations for 3D printed concrete structure, and some real-world application as a case study. In conventional construction, concrete is renowned for its remarkable compressive strength, but is considered brittle in nature. The tensile strength of concrete typically falls within the range of 5 to 10% when compared to its compressive strength. Once a crack initiates, unreinforced concrete exhibits limited capacity to stop further crack propagation, making it susceptible to easy fragmentation without additional reinforcement. The modern structures utilize a material for reinforcement that possesses greater tensile strength or permit more strain before the fracturing compared to the concrete matrix. The choice of reinforcing materials varies depending on the intended purpose, as reinforcement serves not only to improve the structural strength, but also to prevent brittle failure, facilitate the stress redistribution, limit deformation, and crack width. For example, commonly used reinforcement materials include structural or high-strength steel, which is prevalent for enhancing strength, as well as the synthetic fibers made of a diverse range of substances such as polypropylene, which is a PP, polyvinyl alcohol called PVA, glass fibers, carbon fibers, and some more. The need for reinforcement in 3D concrete printing remains consistent. As we talked about in week 4, the main technical issue that reinforcement tackles is the brittle and orthotropic behavior of printed elements caused by a lack of fusion, which is also called LRF, between the adjoining layers. To refresh your memory, this lack of fusion creates a weak connection between the layer, and that is made evident by a difference in mechanical performances between the intralayer. Intralayer is the bulk extrusion, or can be seen as a filament, and the interlayer region between adjoining layers. Due to the relatively new nature of this field, many advancements or investigations into methods for strengthening extrusion-based concrete printing are not entirely well established. However, we can categorize the reinforcement approach into 4 stages. Number 1, pre-printing reinforcement. Number 2, reinforcement during material preparation. Number 3, during printing reinforcement. Number 4, post-printing reinforcement. The printed object can be reinforced in 4 directions: the print path direction, perpendicular to the print path, the print plane, and the plane perpendicular to the print plane. I will provide you 11 unique reinforcement strategies for extrusion-based concrete printing, which are mainly documented in the literature. 1 for pre-printing, 1 for material preparation, 6 for during, and 3 for post-printing. There is 1 pre-printing reinforcement strategy. This strategy to provide orthogonal and longitudinal reinforcement presented by a Chinese construction company. Before the printing process commences, a reinforcement cage is erected manually. This cage is then enveloped by both sides through a layer-by-layer deposition method, facilitated by a dual-node system. It is crucial to note that specific data regarding the mechanical performance of this object has not been publicly disclosed. Still, this reinforcement technique closely resembles conventional reinforcement concrete construction practices. It holds promise for the efficient construction of vertically ascending elements. However, it is important to recognize that the extent of automation in construction and the feasibility of creating non-rectilinear elements may be restricted by the application of this strategy. The second strategy is fiber entrainment. Fiber inclusion, which is a reinforcement method during material preparation, has demonstrated as a seamless integration into extrusion-based printing process. This is evident from the substantial number of publications devoted to fiber-reinforced 3D concrete printing. The addition of fibers are done similar or identical manner to the fiber-reinforced concrete. Depending on the fiber type, length, stiffness, and volume, amount of volume, the material behavior changes. It should be noted The use of large volume or stiff fibers can present challenges, such as the potential to obstruct or damage the pump or hose. But fiber inclusion stands out as a viable means of enhancing reinforcement during printing processes, aligning with either the mixing or extrusion stages. Importantly, this strategy is not labor-intensive and is relatively time-efficient, often seamlessly integrating into automating processes. As a note, it was found both flexible and stiff fibers preferentially align with the filament flow directions. However, it's improbable that fiber inclusion will replace a continuous bar reinforcement when considering load-bearing capacity, as fibers form unconnected networks. Additionally, given that fiber is probably aligned with the print path direction, the strategy is probably limited to providing longitudinal reinforcements. The next one is cable entrainment. Cable entrainment is one of 6 during printing reinforcements. This involves the automatic entrainment of a cable through a cable spool and a stepper motor extruder that is mounted to the end effector near the nozzle. During printing, the cable is unwound by a stepper motor extruder and entrained at the nozzle. A cable with a low bending stiffness is utilized basically to facilitate smooth extrusion at the nozzle and enable it to conform to the freeform nature inherent to 3D concrete printing. Additionally, it is imperative for the cable to meet the standard reinforcing criteria, including strength and ductility. However, it is essential to note that this approach to reinforcing printed elements has limitations in terms of its efficacy, as it does not extend to bridging the interlayer interfaces. In other words, it exclusively provides reinforcement within the single individual layers. The next one is mesh reinforcement. A recent proof of concept for introducing both longitudinal and orthogonal reinforcement has been introduced by a research team at Swinburne University. In their innovative approach, a galvanized steel mesh is incorporated during the printing process using a specially designed split nozzle. The mesh strips are strategically overlapped on each consecutive layer, ensuring that 2 strips are layered atop each other, creating a cohesive structure continuum. This strategy effectively incorporates both orthogonal and longitudinal reinforcement. However, it's important to note that the inherent low stiffness of steel mesh results in limited ductility when subjected to flexural loading. The following approach involves the utilization of steel fibers to establish a connection between deposited layers. A research team from Stellenbosch University has demonstrated the implementation of orthogonal reinforcement using straight steel fibers. Throughout the printing process, modified steel fibers are introduced perpendicular to the interlayer interface with a 10 mm overlap between previously inserted and newly added steel fibers. Worth noting that this method primarily reinforces the longitudinal direction. However, this study observed that specimens reinforced in the manner exhibit a post-crack softening behavior when subject to the flexural loading parallel to the interlayer interfaces, as opposed to the brittle failure observed in unreinforced specimens. The design freedom of extrusion-based concrete printing is not hindered by this strategy, and could theoretically be automated by a device attached to the end effector. The next one is called a nail reinforcement. A French research team led by Professor Parrot introduces a novel concept of nail reinforcement, which is a similar principle used in aforementioned straight steel fiber links. In this approach, 30 mm nails with a 1.8 mm diameter are strategically positioned orthogonally at various orientations across multiple layers after the initial deposition. The study also examined the influence of surface roughness by comparing smooth and the rough nails. Nail reinforcement has demonstrated its effectiveness in enhancing post-peak ductility in specimens subjected to 3-point bending the test, parallel to the interlayer interfaces. It is concluded that post-peak performance is increased by a nail orientation and also the sufficient surface roughness of the nail to ensure bonding with the cementitious matrix. Similar to the steel fab links, the insertion of the nail reinforcement can be seamlessly automated through robotic placement during the construction of the object, leading to potential reduction in construction time. The following approach involves the direct incorporation of steel rebars into 3D printed objects, similar to the previous two methods, but utilizing conventional reinforcement steel rebars. Based on the literature, printed objects are reinforced with 8.15mm nominal diameter bars, positioned orthogonal and longitudinal to the print part direction. The primary focus of the study centered on assessing the pull-out strength of the steel rebar, with not much of saying about mechanical performance stemming from this particular reinforcement technique. However, it can be hypothesized that this approach may yield enhanced mechanical performance given the great geometric properties of the reinforced material when adequately integrated. The next strategy involved additive manufacturing of steel. A simultaneous gas metal arc welding additive manufacturing during 3D concrete printing was proposed for a reinforcement strategy. The proof of concept is aimed at automating the reinforcing process through additive manufacturing orthogonal steel rebar that crosses interlayer interfaces. The welding additive manufacturing has been known by a Dutch company MX3D as used before to additive manufacture a stainless steel bridge in Amsterdam. This method used a 3-axis CNC machine fitted with a machine welding torch at the tip of the nozzle, and vertical reinforcement of bar specimens was produced for uniaxial tensile test. The printed rebar with an 8mm diameter produced around 20% reduction in the mechanical performance of the conventional rebars, but it was sound enough for a structural reinforcement. Design freedom is inherently furthered by reinforcement printing. However, the practicality is not fully addressed yet. Let's jump off to the post-printing reinforcement technology. So external reinforcement, one of them. A study proposed a method for printing a concrete beam in multiple segments with an open reinforcing node. Subsequently, the beam is assembled using an external reinforcement network comprising protruding threaded rods equipped with main thread connectors and hexagonal pipes on either side of the beam. The beam's design is rooted in the strut and tie method, aimed at reducing material consumption and accentuating the design flexibility inherent in extrusion-based concrete printing. This reinforcement approach enables the optimization of concrete segments in a topological manner, minimizing material usage while maintaining structural performance. However, the process of reinforcing and assembling of the beam may prove to be too complicated and time-intensive. Furthermore, the reinforcing material is exposed to the environmental conditions, raising concerns about durability. The next one is called the permanent former. In many concrete printing endeavors, the printed objects serve a dual purpose as permanent former and the structural elements. After the completion of conventional concrete 3D printing, passive conventional steel reinforcements are manually positioned. Once the outer shell has solidified, inner field concrete is poured into it. In this scenario, the design flexibility will inevitably be limited to accommodate the rectilinear reinforcing materials and causing service ducts. Additionally, there is an expected construction time delay as the outer shell must first be printed and reinforced. Due to its relative simplicity, this reinforcement approach has been employed to execute numerous large-scale projects in practical implications. This is readily observed in construction projects undertaken by 3D concrete printing companies such as Cobalt, Peace-Corps, Icon, Cybe, and others. Finally, the last one, post-tensioning. Post-tensioning reinforcement has found extensive application in bridge construction, where concrete block segments are tightened in the direction of the bridge span. This very mechanism is now being employed in the field of 3D printed concrete objects. Here, concrete segments are 3D printed, subsequently assembled, then subject to post-tension using high-strength steel cables. Examples can be found in post-tension 4-meter long 3D printed concrete girder a pedestrian bridge, and a bench. While this technique benefits from its familiarity to traditional constructors, making it easier to implement it still entails labor-intensive work and a time-consuming process. And there you have it. We've reviewed a total of 11 distinct reinforcement strategies based on the existing literature. These strategies can be implemented individually or in combination with others. Given the dynamic nature of 3D concrete printing as one of the most actively researched fields, it's worth noting that more innovative and effective reinforcement technology may exist but have not been covered here. I hope this overview has provided you a foundational understanding of various reinforcement methods for 3D concrete printing. In our next video, we'll deal with the structural design considerations for 3D printed concrete objects. For now, goodbye.